Welcome to week 2 of the Haskell course on NPTEL. In this lecture, we will look at recursive functions in Haskell. We've already seen a glimpse of recursive functions in the lecture last week and in the demo, but let's recall it anyway. A recursive function is one where mathematically there is a base case. Let's consider just integers for the moment. A base case is given, which is f of 0, and you define f of n in terms of f itself. Okay, you define f of n in terms of the value of f on smaller values of n. You define f of n in terms of f of n minus 1, f of n minus 2, etc., all the way up to f of 0. You might not use all of these values, you might use only a few specific values. A standard example is factorial. Factorial 0 is 1, factorial n is for n greater than 0, its n factorial is n times n minus 1 factorial. Another example would be what is called the Fibonacci number, or what is more accurately known as the Pingala number. This is of 0 is 0, let's say. Here you define the function on n in terms of the function value on two smaller numbers, two smaller arguments. Okay, fine. So let's see how you can program this in Haskell. Factorial, as we already saw last week, there is a difference between int and integer. If you want accurate values, where if I want to compute factorial of 1000, let us say, I'll use integer instead of int. So integer, arrow integer. Recall that you write functions by writing the input types in a line. Suppose your function is 3 inputs, each of type A, B and C, and the output is of type C, then you will write A, B, C in a line, and you will write D, and you will put arrows in between. Right? Similarly, here there is one input which is of type integer, there is one output which is of type integer. So you write the two types and you put an arrow in between. So factorial 0, so we are using pattern matching to do this definition. Factorial 0 is 1, factorial n is n times factorial n minus 1. This is exactly reflecting the two clauses of the definitions here. 0 factorial is 1, n factorial is n times n minus 1 factorial. So that's exactly transcribed into two lines here. This is a multi-line definition. Each line caters for some particular pattern of the input. Note that this n is a general pattern. All values of integers will match n. But recall that pattern matching in Haskell happens from the first definition till the last. So it will go in this order. So if I give factorial of 0, it will match the first definition and I will immediately get 1. Note that there is a problem if factorial 0 goes to the second definition, because you will define it as 0 times factorial minus 1, and factorial minus 1 is minus 1 times factorial minus 2, and it will keep going on without any end. Okay, so it will not terminate at all. Right? So it is good that Haskell matches it from top to bottom. It is also imperative that we give our definitions in the correct order. Suppose I had changed the order here, suppose I had put this first and that second, then factorial of 0 would have matched this line of the definition, and then it would go on without terminating. Okay, fine. So for instance, factorial of 40 is this huge number, and as we know, if you type this in GHCI, you will get the accurate result, even though it's much beyond 2 power 63 minus 1. Okay. So int has lower and upper bounds, as we mentioned, minus 2 power 63 and 2 power 63 minus 1 on a 64-bit machine. Okay, so you can write the same factorial function in different styles. Okay, factorial, I can use if then else. I can say factorial n is if n equals 0, then 1, else n times factorial n minus 1. Or I can use, instead of using pattern matching, I can use guards. Recall that guarded definitions, there are multiple clauses in a definition and each clause is guarded by a conditional expression. So, this part of the definition will apply only if the argument satisfies this condition, and the condition is here a very simple condition. I am saying n equals 0. Recall that I could do with guarded expressions, I could do things like XOR B1 B2, and I can say if B1 is equal to B2 then return false, otherwise the value is true. This is a complex condition, right? I am not just checking whether B1 fits a certain pattern of Boolean, I am checking whether B1 and B2 are the same, okay. That is much more than asking whether B1 is equal to a constant. Yeah, in this case of course pattern matching suffices to define this factorial, but I will still write this condition. So, just to illustrate that I can write it in different styles. So, this is the guarded definition style. This is if then else. I can also use case. I can say factorial n, case n of, if n matches the pattern 0, you return 1. If n matches any other pattern, you try to do n times factorial n minus 1. Okay. Note that in pattern matching and in case you cannot give complex Boolean expressions on the left, you can only give patterns. Whereas in if then else, I can write complex conditions here. I could also write XOR B1 B2 as if B1 equals B2 then false else true, right. That is a complex Boolean expression. I am not just checking whether B1 is equal to some constant value, but I am checking whether two Boolean values are the same, okay. So, just to illustrate that you can write the factorial function also in multiple styles. Let us get back to the definition. Factorial 0 is 1, factorial n is n times factorial n minus 1. As I have alluded to before, okay, there are two things to notice. Note the parenthesis around n minus 1, right. Normally you would write, recall that in Haskell you will write f, put a space and then write x. In mathematics you would do f applied on x. Of course, in mathematics you would do f applied on n minus 1. In Haskell you have to say f space n minus 1, and the parenthesis here is not to indicate that f is a function and it is being applied to an argument, rather it is to tell you that n minus 1, the whole expression is to be treated as the argument, okay. The whole complex expression has to be treated as one value. If you do not put this parenthesis and if you write factorial n factorial space n minus 1, it will be interpreted as factorial n minus 1, okay, and that is again a problematic thing because factorial n is calling factorial of n and this kind of definition will not ever terminate. Of course, I can write such a function in Haskell and it will compile, but it is just that if you try to run it, it will never ever end. We will see this in the demo session for this week later. There is no guarantee of termination even for the program as such, because I could invoke this function with a negative value factorial minus 1, and if you do that it will go on without end, right. Factorial minus 1 equals minus 1 times factorial minus 2, this is equal to minus 1 times minus 2 times, and it goes on like this, okay, without end. Yeah, once again note the parenthesis, because if I just say factorial minus 1, I will get a problem because it will not even type check. How do you subtract a number from a function, okay. So, that is ill defined, okay, you will get a type error if you do that, okay. So, how do you fix the factorial function so that it works on negative values as well? Here is how you do it. Factorial, here is one way to do it. You could for instance say that factorial n, if n is less than or equal to 0, I will always return 1, okay. This is not a very good fix because I mean how do we know that this is a natural way of extending the factorial function? We don't know, it is ad hoc. Okay, this is an ad hoc. Ad hoc extension of factorial to z. Okay, normally the factorial function has domain natural numbers. Now we are trying to invoke it with all integers. Okay, and of course in mathematics you know that factorial is a function that is only defined on natural numbers, but when you write Haskell you don't have there is no natural number type in Haskell. There is no built-in natural number. Yeah, so you can use it in using some libraries, but by default there is no NAT in Haskell because it's costly to provide only NAT without providing int. Okay, and yeah, so therefore if I give factorial of if I give this type to factorial, I can invoke it with any negative number, and that's a problem. Okay, but we have one way of fixing it, which is to say that whenever n is less than or equal to 0, I will return the value 1. Now if you invoke factorial with minus 20, I will get the value 1. Here is another way of fixing it, perhaps more faithful. You say that if n is 0, then I return the value 1. If n is greater than 0, then I do n times factorial n minus 1. Otherwise, the otherwise will take care of the remaining case, which is that n is less than 0. I just say error negative input. Okay, error is a function whose type is string arrow. What is the output type? In this case, it is string arrow integer. But you can also use the error function as part of a definition where the return type is character or bool or whatever. Okay, so technically speaking, error, the type of error is not string arrow integer but string arrow a. What is a? A stands for any type. We will see that, we will see this particular feature where you use some abstract types rather than very concrete types like string, integer, character, bool, etc. We will see that in a couple of weeks. That is a very important feature of Haskell. Okay, good. So this is about the factorial function. Error has type string arrow a, prints the error message and abort. So if you invoke factorial minus 20 now on GHCI, it will actually print this exception negative input. The negative input is the error message that we gave. That exception etc. is something that Haskell prints, GHCI prints. Most importantly, it will abort. It will not try to continue the computation, it will just abort and it will await the next instruction from you. So the input for the error function is the error message, which is of type string. There is no output, but the output matches any type whatsoever. So output, no output, but function okay, good. Let us try to do some more programming. Let us consider one of the earliest algorithms known to us, which is the algorithm to compute the greatest common divisor. This is given by Euclid. How do you do this? You start with two numbers. Let's assume that both numbers are non-negative. So you are given a, b. You are also given that either a equals 0 or b, either a is greater than 0 or b is greater than 0. Okay, or more specifically, it is not the case that these are your input assumptions. A is greater than or equal to 0, B is greater than or equal to 0. It is not the case that A is equal to B equal to 0. Okay. Now, how do you do GCD? You all recall from high school perhaps. GCD of AB is nothing but how long do you go? You keep on going till B becomes 0. Let's give an illustration. Suppose I want to find the GCD of, I don't know, 120 and 72, let us say. This will become 72 and then mod that, which is 48. This will become 48. 72 mod 48 is 24. At this point, this will become 24 and 0 because 48 mod 24 is 0. So, since you have reached 0, you will stop, and at this point you will say 24 is the GCD of 120 and 72, and indeed that is the case because 120 is 24 times 5, 72 is 24 times 3. Let us look at another example, maybe 127, 72, let us try this. In this case, it will become 72, 55. And then from here I will go to 55, 17. From here I will go to 17, 4. From here I will go to 4, 1. From here I will go to 1, 0. So, 1 is the GCD. Indeed, because and in such a case you will say that 127 and 72 are relatively prime. Right. So, these are things that you recall from high school. Let us try to see how you program this in Haskell. Except of course, in Haskell you have to give the inputs the type int or integer, which means that you also have to handle negative inputs. We will assume that it is not the case that both A and B are 0. We will also handle negative integers. So, what if either A is less than 0 or B is less than 0, then I will just call the GCD function on absolute value of A and absolute value of B. Okay. Notice again that we are defining a function called myGCD. Why are we calling it myGCD? That is because GCD itself is a built-in function in the standard library. So, if you just try to redefine GCD, Haskell will complain. And we are just saying that the input are of type, the two inputs are of type integer, the output is also of type integer. Okay, good. So, right. So, if either A is less than 0 or B is less than 0, then you will call the GCD function on the absolute value of A and B. If B is 0, then you will return A. Otherwise, you say myGCD on B and A mod B, right. So, now here is one thing, what if it seems like I am assuming always that A is greater than or equal to B, right, because what I am doing is I am saying GCD of AB is GCD of B A mod B, right. What if A is less than B? Nothing. If A is less than B, then in the first step the two swap values, because remember that if A is less than B, A mod B is equal to A, right. So, for instance, if I call GCD with 1721, then in the first step it will switch and it will become 2117, and after that it will become 174, after which it will become 41, after which it will become 10, and at this point you will stop and you will return 1 as the answer, right. If b equals 0, then a is the value, a is the result, right. So this is what I am doing. So this is the GCD function. abs is a built-in function, part of the standard library. It's of type integer or integer, and it returns the absolute value of an integer. So abs of -3 will be 3, abs of 3 will also be 3. Okay. You can define your own version of abs. You can use guarded commands perhaps. You can, here is one possible definition of abs. You will say abs x okay, that is one way of defining abs. Okay, so GCD is part of the standard library, abs is also part of the standard library. Okay. So here is the next example. I want to check if a number is a power of 5. Okay. So how would we write this program? So let's say, so 25 is a power of 5 because I divide 25 by 5, I will get 5. I divide 5 by 5, I will get 1. 24 is not a power of 5 because I have to use div and not the slash symbol. So 24 div 5 is 4, 4 div 5 is 0, right. So this is the kind of check that I want to do. So I keep doing this. So and if your number is negative to begin with, anyway it can't be a power of 5 because I keep multiplying 5 with itself, I will only get positive numbers. So, and we are only talking about natural number powers of 5, not even integer powers of 5, because then that will be 1 by 5, 1 by 25, etc. So we are not looking at that. We are asking whether if given integer is a power of 5. Okay. So right. So if n is less than or equal to 0, I can go ahead and say false. If n is equal to 1, I will say true. Otherwise, I will first check whether n mod 5 equal to 0. Right. I have to check. In fact, here there is a, if I were to actually follow the program, then I will actually come here and say that I will first try to do 24 mod 5, that is 4, and that is not 0, which means that 24 is not divisible by 5. So I will immediately say that the value is false. Okay. So n mod 5 and is power of 5 and div 5. Okay, this is what I am trying to do. Remember that AND has the following behavior. If the first part is false, and anything is false. So Haskell is very clever. What it will do is, it will not even evaluate this part of the expression. The moment it realizes that this part is false, as soon as n mod 5 evaluates to equal 0, as soon as this check evaluates to false, the AND terminates. The evaluation of the AND terminates, and false is returned as the final value. Yeah, so this is something that is worth remembering. So this is a function that checks whether given input is a power of 5. We can also do this. So, we are starting from n and counting down. We could also start below and count up, even though that is more inefficient, because if n is not even a multiple of 5, you will catch it immediately as you count down. But you can also go from below to reach n. How would you do that? That is another way of doing it. So, I could do is power of 5 equals, I have to say, I have to define two functions for this. I have to say yeah, let me just call this function go for want of a better name. I will start from 1, because 1 is the smallest power of 5, non-negative power of 5, go 1 n. Okay. Separately, I will give a definition for go. Go any power p n is, if p is less than n, then I will try to do go 5 times p n. If p is equal to n, then I will return true. Otherwise, this means that p has gone beyond n, I will return false. Okay. So, there are multiple ways of programming the same thing. Remember that we are not talking about two different styles of programming, we are talking about two different algorithms totally. Okay. In one case, you are trying to start with 1 and keep on multiplying and see if you reach n, keep on multiplying it by 5 and see if you are reaching n. In the other case, you are keeping on dividing n by 5 and see if you reach 1. Okay.